Hello YouTube, what's going on? It's Rocket here, and today I want to present to you a CTF challenge that I thought was quite interesting. So the challenge involved reverse engineering a time server binary where you need to find the backdoor for your friend because he just wants to change the time because he's so bored of staying in class. And what happens is this time server is actually running on the school servers, so your friend downloads a copy of this binary for you to reverse engineer and find the backdoor that a developer intentionally put in there. So let's see if we can find that backdoor. And before we get started, I would like to give a shout out to my friend Toxic Flange and Extent Bogon for helping me out on this CTF and collaborating. Without your help, probably wouldn't have gotten to the point I am right now this fast, so thank you a lot. Alright, let's get to the challenge. So here's the time server binary that I was talking about earlier. The first thing that I like to do is run file against any sort of executable that I get. We can see that it is indeed a 64-bit Linux executable, and it is not stripped. So one of the things that you see when a binary is not stripped means that it has debug symbols in it. So one of the first things that I like to do is run the nm command on it with the -c flag. And what the -c flag means is it's going to take the debug symbols and debangle them. So usually when you compile a programming language source code like C or C++, you end up getting symbols, but these symbols have prefixes and suffixes that make the symbols a bit more difficult to read. So by passing the -c flag, you're actually demangling them. So you're making them more human readable. And I'm just going to dump this into a file called debug symbols.txt. So taking a look at the debug symbols, we see a lot of function calls that look like library calls. And for those of you who aren't familiar with code that looks like this, it's actually Golang. So yeah, you can also confirm that just by searching for Golang. And a lot of this code is library code. We don't really care about the library code because if the developer were to introduce a backdoor, he must have written the code himself. So we're interested in what I like to call user-defined functions. Functions defined by the user developer. And one of those is usually in main. So here we actually have multiple main functions. Well, I shouldn't say multiple main functions, but multiple functions that look like main. That also look very suspicious, like main.timehandler, main.rr, main.e, main.main. Those look like some good starting points. So yeah, I kind of want to get some more information about this binary. So, and kind of get an idea for how these main functions are called. So to do that, I just like to fire up Ghidra. Yep, we will close this. We'll start a new project. Write up Ghidra, put time server. And we got to import the actual binary. Okay. And this will take a while because the binary is actually 10 megabytes. So I'm just going to let that crunch in the background. Yes, it's the analysis part that takes a long time. So yeah, you can see it's a pretty big binary. So while that's running and analyzing, how we can optimize our time is by searching for relevant strings in this binary. Some strings that I find are normally relevant, especially when we're looking for backdoors, are backdoor, obviously, debug, and dev. If you can think of any other strings, that's also great. But I'm just going to look for backdoor in here for now. So I'm going to go strings, time server, and just call this strings.out. So search for backdoor. There's nothing there, okay. So is there anything like debug? There is. So let's take a look. Interesting. One thing that was interesting to me looking at these debug symbols was actually this path right here, the debug/prof, because it is a time clock application, so it is web-based and you can connect to it over HTTP. So I'm gonna keep track of that, and I'm also gonna just go and run the time server and connect to it with curl. So that didn't work because runtime error, index out of range with length 1. So what I would do is I would actually go to the actual school server where, oops, you weren't supposed to see that, where the service is actually running, and paste the path that I found in the binary. And as we can see, this actually brings us to a very interesting page where we can get some more meta information about the actual binary that we're trying to find the backdoor in. So anything backdoor related, anything command line, execute, debug, dev, any of those keywords to come to mind, you want to look at them immediately. So in this case, we have CMD line. That looks pretty interesting. And what we find is the way how the time server executable was actually executed. So in this case, it was executed on the remote server. It executed it with this value right here, which looks very suspicious, especially for a CTF, because it almost looks like some sort of key. So we'll take note of that, and let's try running that in our server locally right here. So we'll go time server with that, then we'll go curl, and hey, we actually get a 404 page not found that way. If we do the same thing with the debug prof CMD line, we should get the command line arguments from how we initialized that binary locally on our machine. Which it did, but it's binary output. So let's dump that to a file. We'll just call it time.out. A great name. And now let's take a look at it. And hey, it looks just like on the remote version of this time server. Amazing. So let's just close this. By now, Ghidra should have finished crunching. So looking back at the main functions, oops, we see a bunch of stuff that could take very long to analyze it statically. And you'll also notice that there are a lot of function calls. Most of the function calls in a Golang binary, actually, it looks like they don't take arguments when they're decompiled with Ghidra. I think this has to do with the way how Golang does its calling convention, because it's optimized to run coroutines, which are a very parallel operation. And it seems like, yeah, I'm not so sure, but either way, the way how they're decompiled, they don't accept arguments, which makes it very difficult to reverse engineer statically this way. So going back to our main objective, we want to find a backdoor. And whenever you want to find a backdoor, like I was saying earlier, is you want to think of certain keywords like development, debug, exec, backdoor. So you can search for any of that. And you can start searching for that with strings. Go search for strings. And maybe, like, of course I'm doing it here, but you can also just run the strings command like I was doing over here and just search for, let's say, we looked for backdoor already and we didn't find anything. And we looked for debug, we got some idea that was going there. Maybe let's look for dev in strings.out. Maybe dev is a bit too generic, because sometimes you might get rdev. But yeah, you do have to enumerate to some degree to find relevant information. But do keep in mind that we haven't looked for exec yet. And exec is a keyword, and it looks like there are actually library calls that are related to exec-related operations. So for example, there's runtime.execute, os.exec.Command, which also looks suspicious. And yeah, whenever you see anything to do with like executing commands, that's usually implies executing shell commands, which can often be abused in a backdoor. So let's search for that in the functions here. Let's search for exec. Like we saw in our string search earlier, like runtime execute, runtime close on exec. But let's look for the command, because in a backdoor you'd have to provide a command if you want to execute it, right? So what I like to do here is we're focusing on the Golang osexec.command function in the library, and we want to find what calls this so we can trace the execution back so that we can figure out the execution path to get to this backdoor, if there is one, because it's just a rumor, right? So I like to go in Ghidra and click on this display function call trees. So what this does is it takes the command that you have focused and shows all the functions that called it. So in this case, osexec.command was actually executed by main.rr, which is highly suspicious because, like I was saying earlier, when we look for binaries, we want to look for user-defined functions, not library code for the most part, maybe except for exec, because that's backdoor related. But what should happen is the user code should call the library code. So in this case, main.rr is the function that's calling os.exec. And here we actually see it being executed. So let's take a closer look to see like what this actually does right here. I'm gonna flip over to my web browser and look up Golang exec. Golang exec. This is another cool trick when you're reverse engineering, is you really need to know the library calls for the binary that you're reversing. It can really help in understanding what kind of arguments are passed and the context that they're used in. So, I mean, in this case, it's kind of difficult because, like I was saying earlier, in Golang, os.exec command should accept an argument, but the way how it's decompiled, it doesn't really show that. So later I'll be doing some dynamic binary analysis to show how we can actually figure that out. Anyways, going back to the web browser, we'll find os.exec command right here. And you'll see that it takes at least one argument. So it takes, obviously, the command and a set of command line arguments to the command that you provide in. And it returns a command structure. So command returns the command struct to execute the named program given the arguments. Simple enough. But what it doesn't say, it doesn't actually execute the command. It creates it, but it doesn't execute it. But, so, could this... Oh wait, sorry, let me switch over. So could this command actually be the function that's executing this? I don't know. It didn't seem to, Ghidra didn't seem to map a proper symbol right here, so we'd have to figure that out with dynamic analysis or through disassembly. And yeah, let's actually load this up in GDB and disassemble the binary to see if the command is actually being executed. Because if it's not being executed, then we've just hit a dead end, and we can just prune that right off the bat instead of moving down the rabbit hole and then trying to search for something when we should have confirmed that, hey, there was definitely no moving forward with this OS exec path because it wasn't being called by any other user-defined functions. All right, so let's do that. So say GDB time server, and then to load the functions into memory, you actually have to execute info functions right here. So that loads all the functions into GDB's memory, and then you have to go disass main.rr. So you get a disassembly dump, and what's cool is that it's actually that command is actually this thing right here, this os.exec dot and then execute, actually resolves to command.combined output. So combined output is actually the, like this command here returns a value, and then you call the combined output on as a method from the object that's returned to this. But looking at the decompiled code alone, we would have never figured that out. You actually have to go and look at the assembly code. If you do know how to configure Ghidra to make that show, I would love to know. So please enlighten me if that's the case. Anyways, let's take a look at what combined output does. Combined output. So combined output runs the command and returns its combined standard output and standard error. So that's handy to know. That's also helpful for debugging, because it should execute the command that is passed to it and then print the result to the screen. So cool. So we've found the backdoor. We've confirmed the backdoor is actually there. Well, I shouldn't say we've confirmed the backdoor is there. We still need to, like, just because you execute a shell command doesn't strictly mean you can actually abuse it. But in most cases, I'm pretty sure it can be abused. So let's try going a bit farther. All right, so what calls main.rr? Oh, sorry. I was talking and I did not flip my screen. My bad. I apologize. All right. Yeah, so I was saying, yeah, that symbol resolves to combined output. All right. So what calls main.rr? Main.e calls it. And main.e is called by main root func1. So we're going to try to get as close as we can to get to executing main.rr. So what I like to do is set a breakpoint on the target function that I want to execute. I doubt it will, but we can try. So we'll break on main.rr. Oops, and run it with the command line argument that we found earlier with our web browser on the remote time server. So that's good. It's running. And we have our breakpoint set on main.rr. So we go curl. I like to go VV. I like to see the verbose output of curl. And it didn't trigger. All right. So right here, I'm just kind of doing a little bit of testing, a little bit of random fuzzing. Because if you can get the HTTP protocol to behave differently, you can potentially trigger different branches of code execution. And it only takes 2 seconds, so why not? Nothing. All right. You might want to try sending a post, but I'm not going to. So, all right. So because we couldn't get code execution on main.rr, let's try main.e instead. Maybe if we set a breakpoint there, we might get some more information. And notice here, we also have another net HTTP request. And just like in main.rr, there was another function that we couldn't really figure out what it was. This one here is the same situation. So what we can do is just go in GDB and disassemble main.e. And we can figure out that HTTP request is actually, this function right here is actually this. Because it's taking an object and then it's calling a method on it. So in this case, it's FormValue. So that's quite interesting. So we can actually go back to this sort of like pseudo C-ish code. And it's saying, hey, if some sort of if some data structure of the OS arguments is greater than 1, then you can actually go into this condition right here. And if this condition is true and this condition is true, then we can get to the backdoor. So we need to satisfy these 3 conditions right here, these 3 branches. And we don't know what this is yet. And we would like to know what this is. But interestingly enough, just looking at this local via static analysis, you'd probably have to do some some digging because it doesn't seem to be set. This local variable doesn't seem to be set anywhere in this function, and it's just declared here. So that kind of threw me off a bit, but we can use a dynamic analysis to figure this out. And then it runs a mem.equal, checks to see what local 18 is, make sure it's not a null byte. And I don't know what local 18 is either, so we'll figure all this out through dynamic. All right. So let's try to resolve the first conditional branch, which is if the OS arguments is greater than 1. And notice that if it wasn't greater than 1, we'd run into a panic index situation. And it also says warning subroutine does not return. So if you remember earlier, I ran this binary without an argument way long ago. And when I sent an HTTP request to it, it crashed. Or at least the thread it was running and crashed. So, of course, it needs to have at least one argument. And I'm very confident that sending an HTTP request to this to the binary and setting a breakpoint on main.e will trigger, because we ended up panicking when we started the binary without command line arguments. So we can probably assume this is true for our situation and for the situation for which the time server binary is running on remotely. So now we gotta figure out this. And I like to go into this sort of view in this scenario. So we need, basically it's this part right here. We start up here. This is just a loop, so we don't need to worry about that. And we don't need to worry about this either, because we've started the program with at least a command line argument, and the program on the server is also running with at least a command line argument. And then we run into this block right here. And then we need to get to this if, and then we eventually need to get this condition to trigger and then call main.rr. That's the goal. So going back to the assembly view, we'll click right here. We want to set a breakpoint on this comparison. So 1c6 in main.e. Do we have 1c6 here? We do. So we're gonna set a breakpoint right here and go continue. And then we're gonna send a request. Command equals ID for fun. All right, so our breakpoint was hit. So we should be pretty close to executing the backdoor, because we know exactly where we are in the command line execution, which in this case we are right here, which resolves to this line. We're currently at this line in pseudo C code. So I like to go disass to disassemble where we are. We are right here. And because we're talking assembly right now, we're talking jump conditions. I like to go to Ghidra's view. Again, this little graph view. And I like it because if it's green, it's saying, okay, if the expression is true, you're gonna jump here. Otherwise, you're gonna take the red arrow. So we want to take the green arrow. We want the expression to be true. So basically the value at RX should be the same value at the register RBX plus 0x18 dereferenced. So let's see what RX is. So it's 0. All right, let's see what RBX plus offset hex 18 is. It is hex 20. So in this case, RX does not equal hex 20. And that's hex 20 looks like it looks like it could either be an ASCII space, or it could be 32 in decimal. So let's look a bit up. What values do we have control over? Well, thinking a bit more higher level at this point, we might think, hey, why would the developer ever write put form value right here. What is this? Let's take a look at it. So what we can see here is form value returns the first value of the named component of the query. Post and put body parameters take precedence over URL query string values. So reading this carefully, put and post body parameters take precedence over URL query string values. So a URL query string values is they're just parameters that you can send with HTTP GET requests. So we can still send HTTP GET here. We don't necessarily need to send a post or a put, but we can if we want. So that's interesting. So form value calls parse multi-part form and parse form if necessary, and ignores any errors returned by these functions. If the key is not present, form value returns the empty string. So it should just return the value of the key that is found here. And just to understand this a little better, I did write a little Golang program to test this out. Oops. So I did a little bit of extra reversing to see what actually happened. So here I wrote http.handlerfunc. You might ask, why did I ever do that? Well, if we look at a backtrace in the executable, what called main.e was main.root.func1, and what called main.root.func1 was net HTTP handler func serve HTTP. So handler func, you can think handler func could also be applicable to this test scenario right here. And most importantly, you get the request.form value. So that's how I came to the conclusion for it, writing a little test program like that. So basically what this does is you send an HTTP request to the server at the path bar, and you pass the form key parameter. And if this parameter exists, then it should print out the value that this parameter is mapped to. Otherwise, it should just give you an empty string. So let's test that. So if you have a Golang developer toolkit installed on your machine, you can just go build server.go, which will give you this server executable right here. I've already built it. That's why you see it back here as well. Let's go server, and it is running on localhost 8888. So we can just say curl http localhost. Sorry, let me move my face right here. 8888, and then go to bar, and we don't put anything. Form value is empty. If we say something like, I think it was called form key. I think that's what I called it. And we'll say form key equals rocket. It gives us the value. Whereas if we give it a different value, like this, it actually gives us nothing. So that's interesting. It's actually a null string. And a null string here could possibly indicate our empty value earlier here at RAX. So, interesting. All right, so now that we understand how that works, why don't we take a step back and set a breakpoint. Actually, we don't need to set a breakpoint. We can actually still look at these memory registers because I don't think because the RSP is still part of the same stack, so it shouldn't have been modified. So yeah, let's take a look at this value right here. Because we're asking ourselves, what is net HTTP request form value supposed to accept as parameters? And if we find the key right there, then we will know what key to send this time server, and then it might start behaving more towards getting code execution towards the main.rr. All right, hopefully that made sense. Anyways, let's take a look at what this is. So, interestingly enough, this value right here, RSP plus 0x8, is a pointer to a string, followed by hex F, which is moved to the memory address offset by 8 bytes right here. And in x64 binaries, you can think of 8 bytes as being a single memory address. So you can look at memory as this is one address, this is just another above memory where you can store an 8-byte structure, and so on. So, but if we remember correctly, request.FormValue only accepted one argument. So looking at the disassembly, we might ask, why did we send one right here, and then why did we load another one? Well, the answer is because when you pass a string, you need to know how many bytes you want to read from it. In this case, we're reading hex f strings, which is 15 in decimal, from this string at RSP offset hex 8 bytes. So enough talk. Let's look at this memory address right here. We can assume it's a string, which indeed it is. And obviously, there's no way that this string here could be a HTTP GET parameter key. However, we do have the offset. We do have the string size right here, which is 15 bytes. So let's just take the first few bytes from this string and say something like echo-n this, and then count how many characters it has. It has 17. So if we truncate the last two, we'll get 15. And we can verify that hex f is actually 15 in decimal. This is just how I like to do it. So hex f is 15 in decimal. Perfect. So what if we use this as the key, we might be able to get some better results. So let's do that. Continue. Instead of saying cmd equals id, we'll say this key equals id. Hit the same breakpoint, and let's see what Rx is now. Rx is hex 2, which is greater than 0, I'd like to say. Last time we did this, it was 0, but this time we got 2, and id is actually a size of 2. So that looks promising. Is the value rbx plus hex 18 still hex 20? Let's see. It is. It's still hex 20. So if we take a look at what was put into RAX, RSP plus offset hex 20 was loaded in there. And if we offset this by hex 8 bytes less, we'll actually get this memory address right here, which is the value of which should be the value of ID if I were to disassemble it. So let's do this. This looks like a string, like I was saying, followed by the size. So go xs, because we want to examine string. And I'm doing it this way because it is little endian on a 64-bit machine. And there you go. It's actually ID and then some HTTP stuff. But we're only taking the first 2 bytes, which are ID. So we found the key and we understand what the key is for. Now we actually need to get the length of the key to be equivalent to the length of hex 20. And before moving forward, we know that there is eventually going to be a runtime.memequal. So it's making another check. And that other check, if we go back to Ghidra, is actually this part right here. So it's also looking for comparing not only the size, but possibly the memory, possibly that the memory equals something as well. So that's cool. Let's try ID, because I know that's 6 characters. We run it, we hit the breakpoint, we disassemble, and I know that we now have 6 characters, so I'm gonna set another breakpoint right here. Continue. And we don't hit it. Sorry, I must have messed something up here. Let's try that again, but be more careful this time. All right, so disassemble. Let's see what Rx is. It is 6 characters. Oh, sorry, yeah. Of course, it needed to be text 20 characters. So let's continue. Of course not. So I'm just gonna do something like, well, make it more understandable. Let's show you what I'm actually trying to do here. So I'm just gonna print hex 20 A's. A is not defined because I'm supposed to do it this way. No? Huh. Oh, because I need to go print. And maybe we'll do Python 3 instead. There we go. So now we actually have hex 20 A's. And we can go put that right here. Right. Now it should work. Okay, so we hit our second breakpoint. Sorry for the delay. All right. So it's calling mem.equal, and it's taking possibly these 3 values here. So let's take a look at the RSP, and then we can just go dump all the memory on the stack. And actually a cool way to do that is with Jeff itself, which is actually this plugin that I'm using right here. So you can say something like context stack, and it will show you the stack. And this is like a cool trick because we can actually see that runtime.memequal, it is indeed taking the contents of offset 0, which is in our RSP. Sorry, it wasn't RCX, but now in RSP. And then at RSP offset hex 8, it's taking the actual command line argument that was passed to the program, which is actually the secret key. And that is why it is so critical to find that during the CTF. And if they are equal, then you can jump to main.e plus 108. Huh. Wait a sec. Yeah, well, I mean, they should be equal because otherwise it wouldn't really make sense. So let's go here. Set a breakpoint here. Continue. Disassemble. And let's see what RSP plus hex 18 is. So we can just go context. Context stack. Hex 18. If we dereference this address, we get this, which, W. Interesting. Okay. Yeah, anyways, we'll know if we hit main.rr or not. So break on main.rr, continue, and we didn't hit it. Okay, so let's try providing this secret key value instead. Let's see if we hit main.rr. So you go continue, continue. Disassemble, where are we? We're still in main.e. And now we are actually main.rr. So we're getting close to defining the backdoor here. And before we move forward here, well, just to refresh our minds on how the backdoor function actually looks like, it does a certain check, and then it will take the command and execute it. But we don't know what command it's trying to execute right now, but we're going to figure it out soon. So let's set a breakpoint right here. Oops. Continue. So I'm not sure if there's some sort of loop going on here, because I hit continue and I'm still hitting the same main.r function entry point. So I'm just gonna hit continue again until I end up hitting my breakpoint, which I finally did. I finally hit the os exec command. Assemble. And now let's find the arguments that are actually passed here. And if you remember from earlier, the os exec command in Golang takes a string and multiple arguments. And each argument is going to be an argument to the command that you pass as the first string. So yeah, let's take a look at some of that memory. The first thing I like to look at is seeing, basically I want to look at all this right here. All this is going to be relevant into figuring out what command is executed and how we can potentially abuse it later on to get remote code execution. So let's take a look at RSP 28 and 30. From our knowledge from earlier, we can probably infer that this is a string and this is the size of the string at this address. Same thing here, this is probably a string and this is also the size of the string because it's offset by 8 bytes on an x64-bit executable. Same thing here. You can see the pattern repeating itself, right? So let's take a look here first. x32xw, because we want to disassemble 32 hex words. And so we get this. And yep, so it looks like we're reading 8 bytes from this memory address right here. So, which is a string. Echo get. So echo get is definitely a bash command and says echo get. And interestingly enough, get is, if you pay close attention, is an HTTP method. So you can send HTTP post, get, options, put, delete, you know, you can probably name them. So, but the thing is, like, okay, we can echo get. Good enough for now. Seems harmless, but we'll keep it in the back of our mind. And now what do we have right here? So we'll say x32xw. We get another pattern. We definitely want to see what's here. Echo get. So same thing. Interesting. Oh, obviously it's the same thing. I should just read the assembly right here, because what it does is it says, hey, you're gonna move this value into RX, and then you move the size of the RX value into RCX, and then you're gonna move REX here and then RCX here. Of course, I should have known that. All right, so let's take a look at RSP, which I can actually do just by context stack. So bash, BCY, but we only take the first 4 characters. So BASH is bash, which is a strong indicator of a weaponizable backdoor. Because, yeah, you're gonna take bash and then you're probably gonna execute something like bash-c. Notice it takes 2, so bash-c, and then echo get. So echo get is 8 characters long, 8 characters there. So what is actually being passed here is bash-c echo get. That's what's happening. That is the command that is being passed. It looks harmless. You might think, oh, well, I'm just echoing the HTTP method right here. What could possibly go wrong? Well, you're gonna find out that lots of things can go wrong. So yeah, shortly after this, what happens is we're at the breakpoint right here, And then we're going to just say os exec.Command output, which is going to take our command structure that we just built previously and then execute it and prints the output to the command line. So go continue. And it echoes get. That's interesting. So what if we said something like, I'm actually going to reset this because I don't want to be hitting like a whole bunch of breakpoints all the time. So I'm just going to take this right here and Control C, exit. It should be time server, set a breakpoint, and then run it with the secret, of course, because if not, we won't be able to get to the back door. Amazing. All right. So instead of sending a get request, I'm just going to send something like options. So we hit the breakpoint, we go continue, and it prints options. So what we should think about here is what kind of input does the potential attacker actually have? And in this case, it is the HTTP method, which is options. So if the binary is calling something like --c echo, and then here you have user control input, then does this mean that the user control input is exploitable? Well, we'll have to figure out soon. So let's say I did something like bash interpolation. So where you actually take a command, like bash interpolation is you can take something within backticks, execute it, and then pass it to the string here. So what this would say is it would go bash c echo and then the result from ID, which actually ends up executing and of course printing the results to screen. So let's try doing that and see if that hypothesis will actually work against this binary. Can we actually execute it, or will certain bad characters be filtered and sanitized by the Golang HTTP library? So what I like to do here is I'm just going to fire up Burp Suite, because in Burp Suite you do have full control over the hex content of your payload. So you can actually send stuff that is not valid HTTP, which is super handy. And in fact, you can even use Burp to attack protocols that are even non-HTTP related, which is really cool. All right, so start Burp. And we do need to listen on port 8081 because our time server is listening on port 8080. And make sure it's running, because if it's not running, you ain't intercepting anything. Okay, so we're going to do this. So the small x feature on curl is for a proxy. So when we go HTTP burp, burp is just a host alias on my Kali machine for 127.0.0.1. I'll say 8081. Set to burp. And I'm just going to hit Control R, forward this to repeater, and then just drop this because we have the one at repeater that we don't need curl anymore for now. So instead of saying options, what if we say ID? We'll send it. We hit our breakpoint. Go continue. And our command was executed. So we have indeed verified that there is remote code execution, but the question is how weaponizable is it? Can we actually get remote code execution on the machine and get a reverse shell? Because getting a reverse shell is the ultimate goal of remote code execution from an attacker's perspective. So if we go back and find, let's say, a reverse shell, I like to go on this site right here, which is Pentest Monkey, and you can find a whole bunch of reverse shells available for use. And you might be like, which reverse shell do I use? Well, you might want to try the bash one because bash is installed on pretty much every Linux system. But from my experience, you can run into troubles where you get bad file descriptors. So this is almost like second pick in my books. Perl is also installed on almost every Linux distribution. I think there's some cases where Linux just won't work if you don't have Perl installed on it. And Python with reverse shells seems to be a bit like it works, but it's a bit. Sometimes your output that you get back to your netcat reverse shell can be a bit weird. So, but netcat works very well. And actually, netcat comes installed on a lot of Linux, like at least it comes installed on modern Ubuntu distros. But the version of netcat that gets installed on Ubuntu distros is not the one with the -e option, which allows you to execute any command. And they obviously do that to make it more difficult for attackers to get into your box, and rightfully so. So I like to use this one right here, where you create a temporary FIFO, and then you kind of like pipe a shell into your netcat, and then the communication is done through a FIFO. Pretty cool. So let's take this one. Go back here. I should have moved my face back down here because, let's get it up here. Yeah, okay. So, yeah, we're gonna take that and we're gonna put this in burp. We're gonna try to execute something like this. And try our luck. So we'll say nc. And actually, in the CTF was actually hosted on IPv6 network. So if you're running nc, you actually have to specify the -6 flag to indicate an IPv6 address. So in this case, for this demo, this here's my IPv6 address. But because I'm doing it locally, it is also a link local IPv6 address, which means that if I want to do anything with it, I actually need to specify the network interface that the victim machine is going to request over. So because I am attacking myself, I am ETH0, but if you're on a real network, I'm sure you could brute force the network interface name, because most Linux distributions follow a standard naming convention for these, and that's a pretty small set, especially for a computer to guess. So yeah, we'll do this. And I like to listen on port 2001. Make sure we have a netcat listener. LVP. So note that I'm using ncat as a listener, not nc. And that's because ncat actually listens on both IPv6 and IPv4. If you were to do this with just nc, I believe it would only listen on IPv4. So let's try this. I like bin bash. It's better. Gives you a better shell usually. So I'm gonna change that. Send. Bad request. So this potentially means that there are bad characters, because if you notice, our breakpoint didn't even get hit. And the way to deal with bad characters is usually to just encode them in some sort. Encode them using a tool that kind of lives on the land. In this case, the tool that lives on the land is the base64 command, which comes installed on most Linux distributions by default. So yeah, if we were to say something like, if we took this command right here, and I'm just going to make a file called command.txt. Set paste. So let's say I'm taking this right here, right? And then I'll just say base64, command.txt, and we get a result. Looks great. So this gets rid of all the spaces, all the slashes, all the pipes, and basically all the bad characters. Though usually when you're doing this sort of exploit development testing, it is a very important step is to actually go and test all the bad characters. So before I move too much forward ahead with this, I do want to figure out what the bad characters are. So a space looks pretty bad, and I think a space is bad because when you, in regular HTTP, you might a regular HTTP request looks like this. So get and then path, or some path, you could say. And then you might have like key equals value, followed by HTTP 1.1 or 1.0. And some of these tokens are actually used in HTTP semantics, like the space is used to delimit the HTTP method with the path with the version number, and slashes are used to determine the path. And a question mark is used to delimit a path with parameters, and the equal sign is also used for parameters. And I would also expect the ampersand to be potentially an illegal character as well, potentially. And we're using multiple of those in here. So when you use base64 encoding, you're getting alphanumeric output that also includes pluses and equals. So we know that. So I'm pretty sure that alphanumeric value characters should be okay. But let's try using a plus and an equals. Let's see if a plus is bad. So let's do a plus. The plus is not a bad character because we still got a 404 page not found, printed it out. Looks good. We hit our breakpoint too. Try an equals. Bad request. So we can, although we can base64 encode our payloads, our encoded payloads cannot contain equal signs in them. So just keep that in mind. And yeah, so let's try this payload right here, which is the netcat one. So I'm just gonna go base64 command.text w0 just to dump it all in one line because it's just easier to copy into my clipboard. So I'll copy that, go back to burp, and then maybe go back a couple requests. And what I'm gonna do here is paste this. Actually, before I do this, I do want to show you that you can say something like get, and then you can call any sort of bash command. I just like ID because it's short and simple. Just send it. We hit our breakpoint. We continue, and we still get code execution from the last command of our pipe. So that is also interesting. And I'm actually going to use this to end up executing my payload. And because what's going to happen is I'm going to take this payload right here. So what's going to happen is going to have something like that, and then we're going to pipe it to base 64D, and that will actually give the command. But then we actually have to execute it. Oh wait a sec, that doesn't seem right. Yeah, it got truncated. That would be bad. So make sure we don't truncate our base64 encoded payload. That'd be good. So we echo it, and then we can say base64 decode, and we actually get our command right here. But now then we just go execute it with bash, and that should execute our reverse shell. So now we actually have a reverse shell. Let's go ID. Yeah. So a local reverse shell right there. But you might notice that I've been using spaces here, and I was talking earlier that spaces may be a potential bad character. So if I said something like ls, for example, I'm actually listing the contents of the directory from which I'm running in. And if I say ls space -l, I should get a different output. So I go send, and I get bad request. And that's because I have the space right here. And you can actually get around the space by using this cool trick that where you can use IFS instead of spaces. So go send, and the command is executed. So the $sign is still a valid character, which means that we can actually base64 decode our payload, which means that we will have remote code execution with a reverse shell. And I'm going to show that right here. So let's take this right here. Take this command. Well, actually just take this right here. And then we're going to say we're going to base64 decode our payload and then execute it. And this should exploit the backdoor to give us remote code execution. So I'm going to make sure my netcat listener is on, because if not, that wouldn't do anything. So ncat LVP 2001, send request. We hit our breakpoint, we continue, and we get a reverse shell. So ID, it works. I can go Control C, and I am no longer in the reverse shell. It may be a bit confusing because I am exploiting my local machine. So I'm going to show you the exploit on a remote machine. However, this remote machine is on, like, I am doing this over IPv6, so I do know for a fact that the interface that my remote machine is using is ENS33, because that's the network interface where the victim machine is actually going to connect back to my attacking machine. So that's why I need to change that right there. And don't forget to base64 encode it. And if you remember earlier, these equal signs are bad news for our payload because we're going to get a bad request otherwise. So what we can do to work around that is you can either kind of change the command itself. So you can just go edit the command, maybe add an extra space right here, or you can base64 encode it multiple times. But if you do base64 encode it multiple times, do remember that you will have to base64 decode it the same amount of times that you originally encoded it. So adding a space seemed to have done something right there. Let's try again. This is a process of trial and error. All right, so that worked. So make sure we get that all on one line. And now we're going to, since we only encoded it once, we don't need to decode it more than once. So we'll just paste that right here. And I'll fire up netcat again. And this time I will be sending the request to timeserver.ctf. So you also have to change this in Burp. So timeserver.ctf. Okay. We send it, and we get a reverse shell. So from the remote machine. And I didn't get this far in the CTF. I got to this point a few minutes after the clock rang. So yeah, I'm not sure. I think afterwards I needed to go change some sort of file like time.json and then be able to get the flag. But if you have a reverse shell on the machine, you can pretty much do anything. So right now I am the Rocket user on the hazard machine, which is an alias for timeserver.ctf. And I go ID. I can go IPA, and you can see that my IP address is indeed different. So here I am actually a different IPv6 address, and I have remote code execution. So yeah, Thank you for watching this video, and I hope you learned something, and I'll see you in the next NorthSec CTF.